This is a collaborative work with many researchers from the US, from Germany, Sasha and Anne also involved in this project, from the University of Southampton, from New Zealand, and Japan, South Africa. So I present this work, but lots of people participated in this project. So the mechanism of earthquake in the main Ethiopian Rift is quite interesting for me because this is a very interesting tectonic laboratory where we can study deformation, active opening of rifting. So this Google Earth imagery shows the main Ethiopian Rift, which is from here, from south of Afar, which is, it's another plate boundary, which is the main interest of my project at GFZ, but now I will talk about the main Ethiopian Rift. So here we have the main Ethiopian Rift, which goes all the way down to the south to the Kenya Rift. And depending on the onset of rifting and deformation, we have the northern main Ethiopian Rift, the central and the southern. So our focus for this talk will be the main Ethiopian Rift. And this is the evolution. We have a schematic diagram that shows space-time evolution of the main Ethiopian Rift. And this is specifically applicable to the northern main Ethiopian Rift. So here rifting started at 11 million years ago. And at that time, we have diffuse deformation. Most of the deformation is accommodated by border faults and diffuse magmatism. And then since 6 million years ago, we have migration of deformation from the border faults to the rift floor faults. And now we have localization of deformation in what we call magmatic segments, which are 20 kilometer wide and 60 kilometer long magmatic segments. And these are active sites of deformation. But something strange happening here because previous studies suggest that about 80% of the deformation in the main Ethiopian Rift is localized in these magmatic segments. But recently this is quite revised, and some suggest that only about 40 to 50% of the present opening of the rift is accommodated by magmatic segments, and the rest is accommodated by border faults. Here we have these border faults, and even deformation outside of the structural rift valley. So with that in mind, I will go to the mechanism of deformation, mechanism of earthquake in the main Ethiopian Rift. Here we use two kinds of assumptions. The first one is that a layer, which is a crustal layer characterized by increased strength, results in more seismicity. This is one assumption. And a little bit different assumption is that a layer, which is a crustal layer, hosts seismicity, hosts earthquake, if the applied stress is higher than the strength of the layer itself. So if we follow this, the second assumption, then it's always important to compare the available stress with the strength of the lithosphere. So one of the main, the most interesting study is recently published by a group of scientists from the US, and they show that the gravitational potential energy in the main Ethiopian Rift here is much higher than the vertically averaged lithospheric strength, because it's already here shown that the residual is very high. So the stress, the vertically averaged gravitational potential energy is higher than the strength. So this explains the observed deformation in the main Ethiopian Rift. But the problem is when they compare their results, the dynamic strain rate with the geodetic strain rate, they see a mismatch. So it doesn't explain the observed seismicity. This is not surprising to us because we already know that the main Ethiopian Rift in the crust, we have variation of strengths. The upper 10 kilometers is characterized by relatively high shear stress, but below 10 kilometers, we have a linear increase in shear stress, which linearly goes to up to 120 megapascal. So this average GPE doesn't explain the depth distribution of seismicity or the depth distribution of seismic moment release. And then why do we see this kind of behavior? Why we have an increase in shear stress, a sharp increase in shear stress below 10 kilometers? This is a very nice schematic diagram again from a previous work, which shows that there is a dike intrusion in the main Ethiopian Rift, in the northern part, where we have 20-kilometer wide zone of mafic intrusion. And this mafic intrusion will result in thermal metamorphism, so that weak minerals will be changed into strong minerals. And then we have a sharp increase in strength within the crust. So the faults show they deform with a higher shear stress. So this kind of average gravitational potential energy or average stress in the crust doesn't really explain what we see in the main Ethiopian Rift. Okay. So with that in mind, we try to analyze the available earthquake catalog. So we use this catalog, which was published in 2006, and this is part of the EAGLE project, Ethiopian Afar Geoscientific Lithospheric Experiment. And they use these 30 broadband stations, mainly distributed in the main Ethiopian Rift and also in the northwestern plateau. And they recorded about 2,000 earthquakes. And the catalog has a very high resolution. They have 600-meter resolution in epicenter and 2-kilometer vertical error. So the earthquake, they have magnitude up to 4 earthquake, and this is a very nice catalog that we have, and we mostly use this catalog because this is the best earthquake catalog we have for the main Ethiopian Rift. So when we see the depth distribution of seismicity, we see that most of the earthquakes are localized in the upper 10-kilometer, and we have some lower crustal earthquake, but mostly in the northwestern plateau. And we have also a match between the border faults and magmatic segments. So the earthquakes are mostly localized beneath the border faults here, and also in the magmatic segments. Okay. And one interesting observation we have from this catalog is that there is a swarm or low magnitude seismicity between 8 to 40-kilometer depths. Okay, so this swarm it shows a cluster in space and time, and the earthquake at these depths are characterized by low seismic moment release and also with a large number. So we separate the seismic moment release, we separate the earthquakes, one beneath the plateau and the one on the main Ethiopian Rift. So we don't discuss this anymore now. Just for the time being, we focus on the earthquakes in the main Ethiopian Rift. And as we see here, these swarms are characterized by low seismic moment release. And we have a peak in seismic moment release at these depths. Probably this is something due to anthropogenic effect. But here we have another peak at 7 kilometers and another peak at about 17 kilometers. Okay. So in order to explain why this seismic moment release shows this behavior, we run a numerical model using aspects. So we build a 2D box model. We use appropriate rheology for the rift. Upper crust is represented by wet quartzite, lower crust with wet anorthite, lithospheric mantle, dry olivine, and asthenosphere is wet olivine. So, and we have this extension. We pulled the box on both sides using this extension of velocity for the rift, which is constrained by geodetic observation and also plate kinematic observation. And this open box indicates area of interest. So we zoom into this area and we try to see what's happening. So one of the interesting things which I would like to explain, because all of you know this, the boundary condition and everything, but here I would like to discuss the friction angle. We chose this particular friction angle, which is a friction angle that varies from 30 degrees to 9 degrees between 0 and 1 plastic strain, and then we fix it constant for a plastic strain larger than 9 degrees. This is mainly because of our previous observation based on inversion of earthquake focal mechanisms, where we showed that the faults in the main Ethiopian Rift are in general strong. So this friction angle is more representative of the main Ethiopian Rift. So after running the model, we have this beautiful result. Here we have a formation of border faults. This is the time 3 million years before, after the initiation of model, which is comparable to 8 million years, because we know that the main Ethiopian Rift started to open at 11 million years ago. So now this is 11 million years, which is in terms of geology, it's the present day. So we have migration of deformation from the border faults to a narrow zone, which is the magmatic segment. And this is very interesting for geologists like me, because we can directly compare this accumulated strain with the geometry of the faults. So the same is here. We have a big border fault, and then at the present day, we have flat ramp structure. So the faults penetrate into the lower crust, and this is the viscosity. And here we have a deformation type. So at present, we have a ductile zone sandwiched between a brittle zone. So we expect high seismicity here, low seismicity, and again, a peak in seismicity. So in order to compare our result from the geodynamic model, we compare with the available geodetic strain rate. So we see here, there is a distributed deformation in the main Ethiopian Rift, where a high strain rate localized in a very narrow zone, but deformation is widely distributed even outside the structural rift valley. The same is true here. Here we have a geologic strain rate for active zone, which is distributed all over the rift, but the peak in strain rate is localized in the so-called magmatic segments or 1G fault belts. So in the beginning, I mentioned that our main interest is to see what controls the seismic moment release and the depth distribution of seismicity. So from the, we further process the results from aspect, and we computed the deviatoric stress. And as you see here, there is a perfect match between a peak in the deviatoric stress with a peak in the seismic moment release. So this zone, 8 to 40 kilometers, is characterized by small deviatoric stress and a small seismic moment release. So our work clearly indicates that the rheology of the crust in the main Ethiopian Rift controls depth distribution of seismicity. So that was a very interesting observation, and our paper got published. Everything was good. Just a couple of days after our paper was published, or maybe a week later, a group of scientists from the UK published a new paper, and they said they reported lower crustal earthquake in the main Ethiopian Rift. So if you see this one, we don't expect any seismicity because the deviatoric stress is very small, and we didn't see any earthquake in this part from the earthquake catalog we used. So we try to explain the lower crustal seismicity. So this is the distribution of seismicity, and this is area where they observed lower crustal seismicity. As you see here, it runs up to 40 kilometers, which is a boundary, a Corman, a Moho. So they have an earthquake that penetrates the entire crust. So as this case, we didn't need to run a new complicated model, obviously, because we have seen that the rheology doesn't explain the lower crustal seismicity. So we try to see how the strain rate controls this deformation. But from our previous observation, we know that earthquake, our model result indicates similar geodetic strain rate. So we plug in these values using this simple analytical approach. We build a yield strength envelope or Christmas tree. And we show that this is for the plateau and this is for the rift. So the observed seismicity cannot be explained by the yield strength envelope. And when we compare with the effective elastic layer thickness in the plateau, because from the previous earthquake catalog, we also observed lower crustal seismicity. But when we compare the maximum depth of seismicity with the effective elastic layer thickness, we see a strong match. So in the plateau, the crust has a long-term strength to sustain seismicity. But this, there is a strong mismatch between the maximum depth of seismicity and the effective elastic layer thickness in the rift. So the lower crust in the main Ethiopian rift doesn't have a long-term strength to sustain seismicity, okay? So what we did was we tried to see the geophysical observation from the shear wave velocity. This is area where we have a lower crustal seismicity and there is very low shear wave velocity. And this is interpreted as accumulation of fluid at that particular depth. So if that is the case, we expect very high pore fluid pressure. So what we did was we simply increased the pore fluid pressure to near lithostatic state and again increase the shear stress. So we have for the fluid to increase the pore fluid pressure to near lithostatic state. We have some geophysical observations that sustain or that support our argument. But for the strain rate, we don't have a clear, we don't have a data that supports our argument. But a theoretical, an ideal combination of this very high shear strain rate and pore fluid pressure can explain lower crustal seismicity. So the rheology doesn't explain it. The only way to explain the observed seismicity in the lower crust in the main Ethiopian rift is when we have a near lithostatic pore fluid pressure and a very high strain rate. So if that's the case, we can use this, this result to quantify the permeability because we can compare it with the so-called seismogenic permeability. So in order for this migration of fluid, in order this fluid migration to induce seismicity, there has to be, this value has to be within a range of the so-called seismogenic permeability. So we use the time since seismicity started and the depth or the distance in which it propagated, and we quantified these two values and we simply plug in here to estimate the permeability. So the permeability we used, we calculated, falls within the range of seismogenic permeability. So obviously the migration of fluid or the pore pressure diffusion can induce earthquake in the lower crust. However, the permeability value we estimated or we calculated is much higher than the permeability value expected in the lower crust. So this obviously doesn't sustain for a long period of time. So it has to be a transient value. So if it has to be a transient value, there has to be a pre-existing fracture. So unfortunately, we don't have a clear idea about the geometry of the faults in the main Ethiopian rift. We have here this relationship fault depth versus fault length. This is a border fault, okay? A big border fault with about 300 meter vertical throw. So this is the elevation model. This is where we observed the lower crustal seismicity, and it runs along north-south, almost north-south direction. So at the end, at the southern end of this fault, we have lower crustal seismicity. So we expect that this fault penetrates deep into the Earth's crust. So the fault will be reactivated because of this pore pressure diffusion. And this is also in a perfect argument with our modeling results, where we see the formation of flat ramp structure. So we use the values we have. We have already the values, the Deviatoric, the shear, the stress, the differential stress value, the pore fluid pressure, and we calculate the deep angle. And then we simply compare with the seismicity, the geometry of the fault with the seismicity, and we found this value, which is 56-degree deep angle. So earthquake follows the deep of the faults. So probably this diffusion of seismicity may reactivate the faults in the lower crust, and that explains why we have lower crustal seismicity in the main Ethiopian rift. Okay, so as a conclusion, upper crustal or upper and middle crustal seismicity in the main Ethiopian rift can easily be explained by the rheology of the crust, whereas fluid migrating from the mantle or the Moho can explain lower crustal seismicity in the main Ethiopian rift. So, thank you.
Thanks a lot, Ameha. I will stop the recording now so that we can ask questions.